All right, so remember the homework is Q section homework they have until today. Tuesday. We're basically on homework 2 now. Remember, there's a. We'll talk a little bit about the end of class. By the end of the day, I think you probably can almost do number 1 through 3, and then probably next lecture or the week after, we'll derive the energy equation. And then the last problem involves a little bit of boundary conditions, but that's just a scaling argument. So we'll probably talk about this next week. So the deadline is not going to be end of this week, or then probably not the end of the next week, be the week after. The quiz, there's 30 homeworks. Grader has a take-home test due tomorrow, and there's so many have not been turned in yet. So we're not going to have it this week. It'll be next week. Next Wednesday. So I will give you the previous professor who taught this never gave out solutions. She only gave out answers because she didn't want next year's class like just copying everything. But I think next year's class probably going to copy everything anyway. So I'll probably just end up giving. What I'm going to do is I'll take the best homeworks and I'm going to cobble those into a solution set and try to redact the name. So I will pass out the solutions this Wednesday online. Yeah.
You had a professor early on that would give you the problems and the answers, so you knew if you got it right if you got that.
Yeah.
But you had to figure out how to get to that.
Yeah.
That was nice. But most of the stuff we did in homework 1, you can't do that because the answer is.
The answer is like we already know it's true. It's like how it's true. And there's on Wednesday we'll also talk. We'll have them fully graded. There's some I'll say it right now. I think people are getting confused. Del squared, for example, del squared u, that's equal to del dot del u. I think here del dot del is a scalar quantity. Some people are basically writing this as how do they do it? They did some really weird thing. Del of del dot u. Which is a vector. It's a really weird one, but these are not the same. We'll go over. I'll make a list of the common errors, and you'll have a chance to ask before we have the very short quiz. Okay. Also, course projects. Remember, we just need 5 ideas due in 2 weeks. I think it's about in a PDF. So just maybe put like the idea and maybe one reference, or I mean these days, modern days, you probably just a link to a video or a link to the paper. And I'll say I can pretty much tell right away if it's going to be interesting to us in the class. So if you can align with your journal club presentation, that's even less work for you. The whole idea is that would try to help you. Who doesn't have a course project partner yet? Some people? Yeah. So that's basically once we do so this is for phase 1. This is phase 1. Phase 2 is going to be like a 1-page document. So in phase 1, once the ideas seem pretty good, I think we're going to make a Google Doc of like all the groups, the ideas, and people can join a group if they think, oh, I want to join this group. People can advertise if they want to lead a project. But every course project is better than final exam, right?
Yeah.
Oh, okay. Okay, so we're gonna do course projects, and they'll be presented the last 2 or 3 days of class. So start asking me about those. I can give you a verbal signal if it's good or bad.
And we can resubmit phase 1 as many times as we change your mind until the.
Yeah, generally we would want to. If you have 5 good ideas, if we talk about it back and forth, it should help. So these are I would say undergrad course projects. I think yours are going to probably be a little different. Like we did this problem of looking at like torques on a dam. So they built this demo with a hinge, and we were able to fill it with fluid. This was a Pascal's barrel course project. There's the story that Pascal used to like take barrels of wine and like put this little tube on top and fill that tube up to like 10 meters tall. And because hydrostatic pressure doesn't depend on the volume of the tube, it only depends on the height of the top fluid, he's able to like burst the barrel. And so these undergrads, they built this, and they basically made this little pressure gauge. Unfortunately, this is broken because pressure gauges, for some reason, don't last very long, or at least the ones they buy. So it always breaks. And there's a little venting hole at the top to make sure that you don't get extra pressure. You don't have to build a demo, but I think having something that has some visuals for the presentation will help. Any questions on the course project or anything? Sorry we came on delaying the quiz, but I do try to accommodate people. I would say last time we had a quiz, we did not have a quiz for every single problem set. Eventually, I got tired of making quizzes. All right. So today I think we can pretty much get to the derivation of Navier-Stokes. So last time we talked a little about this idea that let's just review. So let's just review a little bit last time. Okay, we have this, the Cauchy momentum equation has the stresses, the 9 components of the stresses in terms of basically a pressure and what's a function of fluid deformation. Oops. Okay, which we call the deviatoric stress tensor, tau. And that's a function of basically the gradients of U. Gradients of U also has 9 components, right? Grad U, not grad dot U. Grad dot U would be scalar. Grad provides a vector. Grad U gives you 9 components. Okay, and that's because we said each of the 3 components of U is a function of 3 variables, x, y, and z. So grad will basically put each of these things. And that's what you know from problem set 1. You know, grad of a vector gives you 9 components, where each row is basically a single, all the components of this, all the derivatives in this direction will function of these 3 variables. Now, grad U has a lot of information. We said it has 2 types of information: spin, which is vorticity, and strain. And we'll talk a little bit more about vorticity we're going to derive the vorticity equation next week, or we'll probably do that as an in-class activity because it involves some of the identities. But basically, rotation doesn't cause fluid deformation. It just basically causes fluids to move in space, but doesn't cause them to change in relative position to one another. That's what we talked about last time. And so now we know that tau is not a function of both omega and E. It's only a function of E, because I think Newtonian fluids. Newton said, hey, well, fluids got to basically deform to make stress. If I basically just change the orientation of fluid, I don't get any forces. I've got to actually like stretch a fluid or cause some kind of like flow. So that's when we said we got to figure out how tau relates to this rate of strain tensor E. Okay, and then we have these 4 assumptions that basically they're instantaneous, so there's no functions of time. They're linear, and to make it linear, we had to introduce this 4th order tensor, because E itself has 9 components, and each of the 9 components of tau could be a function of any of those 9 components of E. Therefore, we got to have 81 components. That's why we introduced IJKL.
And is there a name for that or anything, or is that just
the 4th order tensor? No, we don't. It doesn't. Things only get a name if people talk about it enough. And I think since most of the world deals with Newtonian fluids, this would have, for non-Newtonian fluids, each fluid would have a different name, and they're all sort of different. But just imagine there's 81 pieces of information in there, 81 different pieces of information, constants, if you will. Then we found, all right, so 81 different components. Okay, then we started getting to recitation. All right, so let's let's talk about today about those 81 components. All right. So the reason why it has so much weird stuff has to do with, remember, this A having 81 components, that's for all fluids, not just Newtonian fluids. So let's just have like a little aside on non-Newtonian fluids. I think there's a soft matter class in physics if you want to learn more. So if you, Peter Juncker, he teaches soft matter. And there might be something in chemical engineering. Because chemical engineers, in addition to dealing with the oil industry, they deal with the food industry. And food has to taste good, so it has to have all these properties. So I think we will not go talk about it in this class, but I think we already have some weird non-Newtonian fluids, like Cedric, he's doing, you are doing Cedric for your course project?
I'm working with the ciliate, like habituating the ciliate through like some sort of device, like maybe microfluidic device.
Yeah, but like some microorganism with like a tail that moves around. Clearly, like those microorganisms are like, they're probably elongated and they move around, so they're gonna have some of these properties. And this is Ethan in the front. He's doing the microfluidics. He did the talk before you came, so maybe you guys can touch base.
We've been talking.
Oh, you have already? Okay, good. Fluids with memory. So polymers, this is going to look like a little hairball. They have long chains that can be deformed, and as a fluid particle, they'll retain some information about their potential energy, the elastic energy, their bonds, and things like that. So regular Newtonian fluids don't have that. What we call nonlinear fluids. All right, so let's draw a little graph about what this all looks like. So basically, we characterize these nonlinear fluids by having this stress, tau. Oh, come on. And this is going to be the strain, which for the purposes of homework problem 5 and 6, well, definitely 5, we're very, very careful when we do the 3D stuff, but when we do the homework problems, a lot of times you're going to do like a scaling. So strain del U, we're going to write that as a d dt of delta L over L. If you have like a 1D system, okay, like a 1D strain, like delta L, and this is the original length L. Okay, so the time rate that you're pulling this outward. So stress versus strain. So people taking a qualifying exam, what does Newtonian fluid look like on this?
Straight line.
Yeah, exactly right. And it also passes. Does it pass through 0?
Yes.
Yeah. Okay, so this is because. Okay, this is Newtonian fluids. Because Newtonian fluids, we have this relationship that tau equals to mu du dy, right? Where mu is just the viscosity, function of the temperature, but not a function of fluid speed or anything like that. All right, so that's only one line on this graph, but like nature and us being all this other stuff, so we're going to fill this up. So for example, this British rheologist studied Bingham plastics, example, which is this for example, toothpaste. Toothpaste. Then we have basically thixotropic materials. Thixotropic. Another word for that is shear thinning. Shear thinning. There's a special. What is there a common shear thinning material you can think of? Something that gets thinner, like with the more force you have. with it. Motor oil? Why do they want to have shear thinning motor oil?
So that it can get in between the bearings.
Oh, okay. Oh, the forces are higher under smaller spaces, and they want it to coat everything.
Yep.
Okay. Shear thinning is actually the kind of most common type of material. Okay, so let's draw some of these. Shear thinning it's going to have basically is going to look like this. So thinning means like the higher the strain, the less the force. So this would be shear thinning. All right. So in other words, it gets like thin. It gets like less powerful with higher strain. It takes less work to deform it. Okay. That's called thixotropy, which is a terrible, terrible word. Shear. And then there's the opposite, which is a lot, to be honest, there's probably some chemical reason. So chemically, the reason why there's a lot more shear thinning materials is because you can have like, imagine you have elongated particles. They're basically going to get aligned, and when they get aligned, they're easier to flow. Shear thickening is a lot less common. Anyone know a good example of shear thickening?
Cornstarch and water.
Yeah. What do they call that? Who made that name up? It's cornstarch with water. I think they asked like some elementary school kid, what do you want to call this? It's cornstarch plus water. So they also, I think this, what do they, yeah, black. What do they put in bulletproof vests? Something similar, Kevlar, but I guess that's the most common because it's a solid, but they used to have these ideas of putting some shear thickening material in bulletproof vests because the bullet would hit it and then it would get higher stress with more deformation. But I don't think you want to put oobleck in your bulletproof vest. It wouldn't be strong enough. Is there another example of shear thickening material? Oh, yeah. That's also is silly putty shear thickening? I haven't played with it. I haven't like hit it really hard.
I pull it slow, it stretches, but when you pull it fast,
oh, and you can bounce it too. You can bounce it. There's this other professor who just bought like 30 pounds of silly putty and just hung it in his office as just like a I don't know, demo, a long-term demo. And if you put silly putty on a shelf over like a couple of years, it's going to start to like just flow into like this disgusting waterfall. There's a famous the pitch. I'm not sure if this is shear thinning or there's a famous pitch experiment. Have you heard of this longest running experiment in the world in fluid mechanics? They take pitch. Does it come out of a tree or does it come out of the ground, or does it come out of oil?
I think it's ground or like oil based.
It's like it's got like a million times the magnitude of water of viscosity. But basically, the longest running experiment ever, I think, they have this container of pitch, and it forms these drops, and the drop formation takes like 30 years. So I think the original author died, and then they had a second author finish that up. I don't know if pitch is time dependent or which of these it is. All right, shear thinning, shear thickening, and all right, we have one more here. This is Bingham plastic, which I mentioned in the beginning. Plastic. And it's characterized by the fact that there's like a little thing here, which we call a yield stress, which means that it doesn't flow until it gets to a minimum stress, and then it flows. So it acts like a solid, and then it acts like a fluid. It undergoes a kind of like plastic deformation once it flows. So that was nonlinear fluids, and we have non-isotropic fluids. Like suspensions of rods. Isotropic means the force depends on the direction, which probably depends on like the orientation of the little particles. So for example, bacteria, liquid crystals. Okay. All right, that's all we're going to talk about non-Newtonian fluids. Let's talk about the properties of A if it satisfies each of these Newtonian. So back to Newtonian fluids. There's this really old school book called Gallery of Non-Newtonian Fluids. I mean, it's got some really weird stuff. Like there's like the thing if you pour, if you have like an open container and another open container, and you basically like have a string of the of some non-Newtonian fluid, it's called container emptying, but basically it'll go from the top to the bottom if you just wait long enough. But this is it's black and white. It's almost out of print. And it's got some. If you have this rod and you spin it, stuff will climb the rod. Rod spinning. Each of these has a different effect, and basically stuff will climb it. I forgot what that one's called. But if you do a course project on any of those things, I think you could talk a little about this tensor A. All right. So A is isotropic because we're going to be doing Newtonian stuff. And we've talked about isotropic tensors before, but you probably just didn't notice because they were just like such technically like a 1D and a 2D and a 3D tensors are tensors too, except they're simpler, so we don't think of it that way. So for example, so A joins its family of other things. For example, delta ij is a 2D tensor. We've been using that identity matrix everywhere. This is delta ij where the diagonal's on the ones. So this goes 1, 1, 0, 0, right? All right, let's be 3D fluids. 1, 1, 1, 1, 1, 1. All right, that's an isotropic second order tensor. The isotropic third order tensor we encountered that before. That was it was a permutation symbol, which we called when we put it in this format, we called it big sigma. And finally, the fourth rank tensor is this A. One, two, three, four. There's no good book that encapsulates a lot of stuff for graduate fluid mechanics. But if you did want to read about this, there's this Jeffrey's Cartesian tensors book. And I considered giving, but to be honest, the notation in those old books are so hard to follow that I thought we'd just do it all together with a handout. So one thing you might notice is all isotropic tensors of even order. So for example, the second and the fourth are composed of sums of Dirac deltas. All right, I'm not going to show that, but that's what the mathematicians have found. And this is this is an amazing example of, like, I would say pretty abstract math getting used in the real world. Rank isotropic fourth order. All right, so remember we had A, and it's got 81 components, so 3 times 3 times 3 times 3, AIJKL. But this can be written as a sum of deltas. So we're going to have 3 arbitrary coefficients. Delta ij, delta kl, plus lambda 2, delta ik, delta jl, plus lambda 3, delta il, delta jk. And there's a book by Aris, 1962, page 30. That's where I got this. All right, so those 3 constants actually have to do physically with the fluid in this case, and we're going to use the properties of it being linear, isotropic, instantaneous to calculate what these things are. And remember, this thing is used physically in the following. We use A to write the deviatoric stress tensor, which is tau ij, A ijkl, the rate of strain tensor, which is LK. Okay. So when we did conservation of angular momentum, we showed that tau is symmetric. That means tau ij is tau ji. And in terms of A, we can also switch aijkl is ajikl, right? We also know the rate of strain tensor is symmetric. Remember, E was composed of del U plus del U transpose. When you add something to its transpose, it means that off-diagonal elements are going to be the same. So that means E LK is equal to E KL. That means AIJ KL is equal to AIJ LK. So that means from the notation above that we only have 2 coefficients. Lambda 2 is equal to lambda 3. Okay. And therefore we have AIJKL is now just two coefficients that we have to find. Delta ij, delta KL plus lambda 2. I'm going to sum these. Delta JK. All right. So if we consider our deviatoric stress, we substitute that in there, you're going to get this. Lambda 1 So L and K, we need L to be equal to K, so we got lambda 1. When L is equal to K, you're going to get EKK, delta IJ, plus 2 lambda 2 EIJ. So physically, what do these mean? EKK is del dot U. Why is that? Let's think about it. So we got, since, remember, EIJ looks like this. So del dot U, basically, you're going to have basically the J's and the I's equal, so that it just becomes divergence of U. Those you have multiplied by 2 and divide by 2 and multiply by 2. So that's why you get del dot U. So you don't see these lambda 1s and lambda 2s everywhere. Lambda 2, people call that mu, which is the shear viscosity. And lambda 1, they call this, they introduce this idea K. And they call K the bulk viscosity. So all of you know non-Newtonian, you'll learn Newtonian fluids. For Newtonian fluids, well, let's write what tau is, and I'll explain why you never see K. So tau, with these new, substituting for lambda 1 and lambda 2, we're going to have these values. Plus 2 mu E. All right. So the reason why you probably haven't heard of bulk viscosity is because for a Newtonian fluid, divergence of U is 0. For a compressible fluid, you might have heard about bulk viscosity. But anything that's incompressible, we have this del dot U being 0.
You use it a lot.
Oh, bulk viscosity? Oh, okay. Oh, yeah, because that's a pressure. That's a, you got to have compressible fluids to hear sound. Where K, mu are material properties. Oh, come on. They depend on density and temperature. Okay. So review being divergence-free for incompressible fluid. So for, honestly, all the problem sets in this class, you'll be using this. Newton said that basically, hey, we just have to have the rate of strain, which tells you the del U, tells you that basically how much the fluid is being sheared, and the stress is going to be proportional to that. So I think everyone remembered the, I'm going back too far. But for, like, when I wrote that Newtonian fluid, I said tau is mu times du dy. This is basically includes all the different directions. And so if we want to figure out the stress, we just have to figure out the pressure at that point, and we have to figure out the deformation around it to U. Okay. Okay, any questions on what we've done up here? I want to zoom out a little bit. I was thinking of stopping briefly so people could look at like basically how this came, like this lambda 2. This lambda 2. So lambda 2 equals lambda 3. We're basically substituting for, lambda 3 equals lambda 2 here. And then so we're going to have this times these two. And when you actually multiply this by ELK, L and K have two of the dummy coordinates, so we're basically going to do a summation. ELK times this delta KL is going to become EKK, and then you have delta. You just keep that delta IJ there. And this one I think is a little bit not as easy to see because there are two. But basically, you have ELK, and then this becomes EIJ because we have these two things, IL and IL and JK. So that became EIJ. Okay, so we basically have these two things, and then all we've done is relabel them. Instead of calling lambda 2 and lambda 1, we call them bulk viscosity and shear viscosity. And because we don't, this class is really going to be about Newtonian fluids, Newtonian incompressible fluid, which are incompressible. That's 0. So we're going to be using this stress tensor for the rest of the class. So questions on how we got this stress tensor T? All right, so let's I do want to write out what they look like. I don't think I have yet, but you'll probably be turning back to this a couple times as you kind of like make sense of these problems. So and they don't do this in actually the graduate textbooks. And I think it's easiest to always learn the Cartesian system because they're just orthogonal, and you don't really want to deal with r theta z, because r theta z, the derivatives like divergence and stuff like that, looks a little bit weird. So del u, remember, so every new symbol we introduce a new index. So this is del uj at dxi, going from the left. I, and this is so ei from the del symbol, ej from the u symbol. All right. So that's a tensor, and it looks like this. The diagonal is going to have derivatives of that coordinate with those directions, and then here we can have du1 dx2. I'm just going to fill the top row, du1 dx3. All right, so this first top row is basically u1 with those three derivatives, function of x, y, and z, and we got u2 as a function of three derivatives, and then u3. Okay. Now the rate of strain tensor, I need a little more space because we have some of these terms. Remember, rate of strain tensor, first let's just define what it is, just so we remember. Del u plus del u transpose. So I'm going to take what I drew up here and then add its transpose. And I have 1/2 so that I don't have like double stuff on the diagonal. So you can imagine if I take that, the diagonal is going to remain the same because I'm just multiplying by 2. I have 2 terms of divide by 2. So du1, dx1. Just write the diagonals. du2, dx2, du3, dx3. All right. So let's do this. So du1, so we're going to have the first du1 dx2, and then plus du2 dx1. I think that's all I want to write, because it's just going to get too much. But you get the idea. And then t, if I were to really write that, it would be basically negative p, basically times the identity matrix. So pressure is along the whole diagonal, plus 2 mu times that other matrix up there. Or tau ij. This is the force per area in the in the j direction on the face perpendicular to I in j direction. Okay. For example, for this bathtub problem, you're just going to consider like a, okay, you consider like a one-dimensional stress. So the normal stresses, so the diagonals of the stress tensor. T11, T22, T33. Involve, you need to know the pressure and the speed in that direction. Tangential stress deal with shear. We call these the off-diagonal terms. They don't involve pressure. So let's consider like the simple case. And honestly, most of the homeworks are just going to involve 2 dimensions, but when you derive these things, it's easier to do in 3 dimensions. And so anyone you're going to do numerical simulations, you generally want to consider those third dimensions too. So let's say we have this velocity field, ux in the y direction. Sorry, the velocity is horizontal in the x direction, but it changes as a function of y. Let's say it changes in a linear fashion, beta times y. Then the force per area on the bottom surface is going to go like tau yx is equal to mu du dx over dy, and that's mu beta. So it'd be a constant stress. Do they call this Couette flow? When it's like a constant, I think it's a constant, it's a linear, just a constant velocity gradient. I think they call this Couette flow. Couette. All right, any questions on like what this looks like before we write the full Navier-Stokes? Like, are you good with this?
Quick notation question.
Yeah.
Is there a difference between like the capital T and the tau?
Yeah. Back in
That's where that
back last lecture.
comes in, right?
Okay, Cauchy momentum said T. They both have the same units. T has stress. Capital T has stress, but basically we said T had two parts. It had the hydrostatic part, which is given by the pressure along the diagonals, but then it also had a part that depended on fluid gradients, velocity gradients. So we said T was negative P along the diagonal plus tau, which is like if you have flow, you use tau. If you don't have flow, you use just P. That's the difference. T is called the stress. Tau is called the deviatoric stress, but both have units of stress. Other questions on, and that was from last time's notes. Okay. Other questions on, it should be really, really clear that del U looks like this. So I guess with this notation, we basically have J as the rows and the I as the columns, right? So if you understand del U, then E, we're just adding it to itself and doing stuff. We're good? We're okay? Yeah. Uh-huh.
Can you please explain how you get the E here?
Oh, how do we get this E? Okay, so we got this matrix del U, and we added its transpose. So transpose, so for example, del U transpose is going to look exactly, transpose means the diagonals switch places. So the off diagonals stay the same, right? And then this one is going to be du2 dx1, because that's what was here before. So this person went here, and then this person went here, this person went here. So we switched 3 elements. And this rate of strain, so we call E rate of strain tensor. We took the 9 components here and added to its transpose. So, and we divided by 2. So the diagonal ones don't change because they didn't change when you transpose it, but the off-diagonal ones now have 2 terms. Yeah? Yeah. And yeah, good. Any other questions? All right, so because of the formulation of A, that's why this 2 mu, so this 2 mu came out of basically A being isotropic and having those properties. And this is Newtonian, so we don't have the del dot U term. All right, so let's finish this up. So now we have, after all that work, we have this. We basically, we're working with this. Rho du dt. We had the body force plus, Cauchy said, hey, I don't know how to represent all the stresses, so let's just put it as the divergence of some 9-component tensor. Now we noting, so after Newton came in and said, hey, we can write T as 2 parts. One part dealing with hydrostatics, where we just have the pressures, and those are only acting normally. And another dealing with like the simplest possible assumption about a fluid, which that it depends on its velocity gradients. And because it's isotropic, it has a nice form that only depends on E and not on omega. So then you have del dot T equal negative grad P plus 2 grad dot mu E. And luckily, mu does not depend on your surroundings, so we can pull all those out. So if you have a fluid that has a temperature gradient, you're not going to be able to do this, but if you do have isothermal fluid, then the viscosity is going to be constant. Typically, mu depends on temperature. So 2 del dot E, it would be 2 del dot, we substitute this in, 1/2 del U plus, oops, transpose. You can show this with index notation. Maybe that would be good quiz fodder. This is just the Laplacian of U. Okay. And if you want to practice on your own, here's some hints. So the index notation, you can show that del dot del U is del squared U, and del dot del U transpose is 0. So we got the equation of motions for an incompressible fluid now. All right. And of course, you recognize those as the Navier-Stokes equations. We got about 20 minutes left. I think I covered actually a decent amount of material. Do we want to talk about homework? I know that you're probably celebrating after you did the last homework, so maybe you have not finished homework 2 yet.
Certainly haven't finished it.
But I think a little bit of hints along the way will reduce the procrastination at the end. But are you all good with this? I guess as it sinks in, people can ask. All right, so now we're talking about homework 2. All right. I feel like we talked about number 1 a little bit already. So maybe I think that's good for now. Yeah?
Question on 1.
Uh-huh.
You're re-deriving Cauchy's momentum theorem, but you're with a compressible fluid and fluid flow, basically. So the fluid flow velocity is no longer 0, and the
That's
fluid
right.
is compressible.
Yeah, so basically it's going to look very similar to what we did in class.
But you've got to go back and dump a couple of those assumptions that we used.
Yeah, but you're going to have to use this conservation of mass instead of incompressibility. So you have to. So homework 2, number 1, hint. You're going to have to use conservation of mass as one of the assumptions to get rid of terms, to remove terms. And a conservation of mass, if you remember, tells us that we track a fluid particle, the density doesn't change as we follow it around. It says material derivative of rho is 0, which means that's 0. So you'll need to use that, and then you should be able to show that rho du dt. Okay, so the steps, the step-by-step process for this problem Reynolds transport theorem tells us how we basically deal with derivatives on the outside of the integral. It says we can basically take the inside and put it, use this material derivative. So we got d by dt of rho u plus divergence of the flux through the boundaries.
I didn't think we could do that if v wasn't constant.
By v, you mean volume? No, Reynolds transport.
You now got a deformable moving volume.
Yeah, Reynolds transport is actually valid for deforming volume.
That makes things much easier,
Yeah.
because I was spinning around with that.
Valid for v of t, which is a moving deforming volume. So I don't know, if you have a basic v of t, it's like a, I don't know, a vapor's smoke plume, and it's basically moving around and expanding and stuff like that. And there's flows going through it. All right, so what you're going to do, I recommend you do after this, if you haven't started this, you're going to expand this out. Expand both of these out. And you should get 1, 2, 3, 4, 5 terms, right? Expand to 5 terms. Collapse some using conservation of mass, and the rest go as we did the previous derivation. All right, number 2. All right. Part A, show that, all right. So number 2A, basically, we've given the equations of hydrostatics, which says that, hey, our pressures, it doesn't have to have all the deviatoric stress. It doesn't have to have any function of velocity, because all the velocities are 0. So we basically have the gradient of the pressure is rho times g. Physically, what does that look like? It means dp dx, dp dy, and dp dz is equal to 0, 0, and negative rho g, for g is equal to negative g z hat, which is our typical thing, like, you know, water surface, you got z going up, g going down. Okay. And you have p equals 0 here, and then here you're going to have p equals to negative h. Okay. All right, so physically, that's what this matrix looks like. So show that, so part A, you're supposed to show that we can write it as any position. P of x can be written as P naught plus rho g dot a position vector x. Okay. All right, so this, I would just, you know, use the Taylor expansion, which we've done a couple times before, P naught plus del P dot x. This is Taylor expansion. And then plus order x squared terms, which you're not going to, and then basically just do a substitution. So that should be, part A is basically just a one-liner. Part B, you're going to have to use this formulation for the force. So they say for an arbitrary body, or arbitrary shape, you have where ends the outward normal to the fluid. This is the body, and this is the fluid. So it goes into the fluid. And then torque, which we use this L naught notation, cross N P D S. I guess in the homework I've been calling it A. That's fine. All right, so this one is also this one you basically, so we define some position vector here, x, and there's actually, I think if you just write these two and substitute for rho, I think it's basically not so bad. All right, part C, use the divergence theorem to figure out Archimedes' principle. Archimedes' principle, he went into a bathtub and then like he shouted out with glee and then he ran through the streets naked. Basically, Archimedes' principle says that the buoyant force in the body is equal to the weight of the fluid submerged. Fluid, not submerged, but it's basically displaced. Sorry, displaced. So the key things: the buoyant force is not equal to the weight of the body. The weight of the body is the gravity. So, like if you have some body here, you got two forces. You got one that's mg, and then you got the other one, which is basically, I don't know how to draw this, fb. And F buoyant force is equal to rho g times the volume, because rho g is the this is the density of water, not the body. So that's why if you go to the Dead Sea and you go swimming, the salt water there is like super saturated. It's like at least 1 or 2 or 3% higher than regular water, and you feel like I think anyone can swim there because pretty much everyone floats because you get that much more buoyant force. But you'll be covered in salt, so you probably don't want to swim there. I think they have a sign that says "Don't swim here" because, like, if you get any of that salt in your eyes and your mouth, it's like pretty gross. And unfortunately, like all our like limited lakes are becoming like dead seas and emptying. There's like a lake in Africa or the Middle East that's becoming like totally drained because we're taking all for agriculture and everyone's wasting and using more water. All these lakes are just becoming dry deserts, and because the bottom of the lake hasn't seen the sun for millions of years, so all this sand is basically going in the air, and everyone's getting like lung problems because of our overuse of water. Okay, so how are you going to do this? F. We have this. You're going to take this. You can take this as a given. So given. This is the definition of force. Of hydrodynamic force. I call it hydrodynamic because it's true in general, but for the special case that P is just rho g is hydrostatic. So with the divergence theorem, you can write it like this, and then you can do the rest. You need to show that F that is equal to rho g times the volume. Okay. Okay. So, maybe I'm going a little too fast. Questions so far? Archimedes' principle. I've been kind of lazy with these vectors. Let's just say the magnitude of the buoyancy force is equal to this, and that we want to show that it's equal to the buoyancy force. But it's clearly upward. So basically, you want to substitute for del P, and then you should be able to get it. Questions on these homework problems so far? All right. And the next few lectures, there's not going to be too much on vorticity, but part 3 on the homework has to deal with the vorticity tensor, and the vorticity vector. All right, 3. Half. This is big sigma. So that's the big sigma, which if you remember, it's epsilon I, j, k, ei, ej, ek. All right, so
Yeah, your big sigma and your epsilon.
they look, that's why we need to go over this. And that's the vorticity tensor, and this is a vorticity vector. Remember, one of them is a vector. For like a purely rotating fluid, like a steady state motion, like if I put something on a record player, that omega, as we'll talk about, is just going to be like vertical. But basically, you need to show in the homework that if the following relationship is true, then this relationship is true. Omega is equal to negative big sigma double dot omega. Okay. And you want to do this with vector with the Einstein notation. I gave you the definition of big sigma here, and omega, it's our.
Is that like your rotational
Yeah,
velocity?
it's the del U minus del U transpose. And because of that, it's del U minus del U transpose. It has the following property, where omega ij is equal to negative omega j I. I think we call this anti-symmetric. All right. Okay. So what I would do if I were you, I would start like this. IJK, EI, EJ, EK, double dot omega. Remember, every new index, we have a new notation. So omega LM, EL, EM. Okay, that's what I suggest you start like that. And remember, this double dot is like, it's like having one dot, and then because that dot obliterates these two, then the second dot obliterates the other one. Okay. It's like literally like having two dots, but you got to take care of them one at a time. And it's like peeling an onion. An onion of math. Hopefully it will not make you cry. All right, and the second one, you can do it like this. Maybe this is getting too pedantic. Yeah, you need some index notation for this. I think I got to save you some for next time, because otherwise, I think your brains are full. I think your brains were probably full 30 minutes ago, but yeah. Today's 11th. I think we can probably keep it for now. As we get closer, we could probably extend it by a few days, but we are making next lecture. I'm going to derive conservation energy, and you'll pretty much know how to do every problem but one. So maybe it'll be delayed by 5 days or 7 days, but it will be due. And now I'm going to pass out homework 3 soon. Yeah. Okay. So start you've finished the other homework. Start this homework, especially if it's fresh and I explain it to you. I'm getting some homeworks that are like incomplete. In the long run, that's going to be an issue because each homework is going to build on each other. So there's a group that meets after this class, right? Who's the leader of that group?
Well, we're not really leaders. Just me and Felix and Almeida, and there's, yes,
Okay.
we all get together at the Love Center Atrium, or the Love Building Atrium.
The bottom floor?
Yeah.
Bottom floor. Okay, so this is Don's study group. And this is Mondays and Wednesdays too, or just Mondays?
Monday and
Wednesday, at what time?
11.
At the Love bottom floor atrium?
Yeah, and there's I made a little study group in Canvas, so we can drop files between each other and that kind
Canvas or Teams?
Canvas. You can actually go onto Canvas, and if you look under groups, there'll be a study group. It's got that information. As I could,
Yeah. Because I think some of you are commuters and stuff like that. Some of you, so please work with each other. On the homework, I encourage people to talk to each other. When you write it up, you probably want to have some idea what you're doing, just not blindly copying. So, but have someone to talk to and work it out. There's like whiteboards over there. You can also do it online, but at some point you'll need to have someone to talk to because we have 6 homeworks. We have 6 homework sets, and we're only on the second one. Work on your course project ideas. Remember, send me that stuff. And I'll see you next time. Who's doing the presentation? Someone presenting next week? Do we skip a week for the journal club? What are you guys going to talk about?
The tea-leaf paradox.
What paradox?
Tea-leaf paradox.
Oh, the tea leaf? Okay, that sounds pretty mysterious. Can you, maybe bring us some demo or something, or video. All right, so, yeah, the tea leaf paradox, that's perfect. Already has my attention. Please, is it the boundary layer one? Is it the boundary layer thing? Sorry? Is it a boundary layer thing? Because there's a demo where you basically put tea and you spin the fluid. Oh, okay. All right, I won't say any more. And if you do a physical demo, I'll give you like 2 or 3 more minutes at the end. I won't rush you through it.